Hello everyone, welcome to the Litmus video tutorial. I am Karthik, one of the maintainers of the Litmus project. In our previous episodes, we talked about the concept of cloud native chaos engineering, how Litmus enables you to perform cloud native chaos, and we had an architectural overview of Litmus, and we got started with a pod delete chaos experiment. In this session, we will talk about the Litmus components in more detail, how they are integrated, and how they contribute to the overall experiment execution. In that process, I'll also take you through a brief tour of the GitHub project of Litmus. We will take a look at the various repositories within the LitmusChaos project. And I'll also introduce you to the initiative called Special Interest Groups within Litmus, where the community members are aligning themselves to the groups working on these components and contributing to the roadmap of these components as we go ahead. So with that agenda, let's get started. Let's take a look at the agenda. So we have a small recap of the LitmusChaos flow from our previous episodes. And then we'll go on and discuss the components or the moving parts of Litmus. We've categorized these components into different sections. And today we'll talk about chaos orchestration and execution and monitoring. Under chaos orchestration, we'll talk about the chaos operator and the chaos runner. And we'll also take a closer look at the experiments. And we'll talk about the metrics and event exporters that we're using in Litmus. And followed by this, we will introduce Litmus special interest groups. We'll take a look at the charter of one of the SIGs, talk about the objectives of these SIGs in general, and also talk about what the future is and how we plan to increase the participation and community representation in these SIGs. On to the recap now. So by now, you're already aware that the chaos experiment, the chaos engine, and the chaos result are the primary custom resources in Litmus. There's also the chaos schedule, which you were introduced to earlier. We'll talk about the chaos schedule in another episode. For now, let's focus on the chaos experiment, the engine, and the result. The chaos experiment, as you know, is a low-level definition of the chaos experiment itself. It talks about the chaos parameters. It talks about the libraries that are made use of to run this experiment, the permissions associated with this experiment, some operational characteristics such as what is the security context, do you need privileged mode to run this experiment? Some of the experiments do. Do you need to specify the host PID to true, etc. And this also contains the default values for the experiment tunables, say the chaos duration, the interval, and a few other characteristics are all available as defaults here. These are available off the shelf and are pre-built, and this is something that you pull from the Chaos Hub. Next up is the Chaos Engine, and this is the user-facing CR, and this is where you bind an application instance with a chaos experiment. And you also define certain run characteristics, certain run policies. And this is the one that holds the status of your experiments. It can also override some of the default characteristics of the experiment, some of the default tunables that you have set in the chaos experiment CR. This is the CR that is reconciled by the chaos operator and is the first one that is going to be installed by the user when he wants to trigger an experiment, provided the experiment CRs have already been pulled. The chaos result is something that is runtime created. The experiment creates this resource and it holds details of the experiment run, as in what is the verdict of the experiment, what is the status currently, and what is the nature of the experiment result. Sometimes you want to push custom results out onto the CR. Say you want to push out the number of failed requests or the total IOPS or the latency or throughput or some other attributes that you want to be represented as part of your experiment run. That can be pushed to the result. With that knowledge, let's take a look at the runtime flow, which we talked about earlier. You have these components, the operator and the metrics and events exporters. You have the CRDs. You have the hub from where you pull the experiments. The first step you do is you install Litmus via manifest or via Helm install. That creates the CRDs and the operator. Then you pull your experiments from the Chaos hub. They are available in the form of YAMLs. On the hub, you push them into the cluster as CRs. And after that, you're actually going to create the Chaos engine, which binds your application instance with this Chaos experiment. Your operator, which is watching for this Chaos engine, is now actually going to launch the Chaos runner. The Chaos runner, in turn, is going to create the experiment jobs, one or more experiments, depending upon how you have constructed the Chaos engine. That is followed by the Chaos result creation. The jobs create them, and the runner looks at this Chaos result and patches the Chaos engine. And there you go. That's about the flow of your experiment. We'll come to the orchestration part of it. The first component that we'll discuss today is the operator. And in this slide, I've got a pictorial representation of the operator's functionality. Let's focus on this diagram for a bit. I have multiple Chaos engines represented by Chaos engine X, Y, and Z. And I have the Chaos operator, which is reconciling these Chaos engines. What does that mean? What does it do? Each of these Chaos engines has, as you already know, a lot of information defined within it. It talks about what is the application you want to induce chaos on, and your operator is actually responsible for identifying the application that is mentioned here in the Chaos engine, whether it exists on the cluster. It does so with the help of the app namespace and app label that is defined as part of the engine. Once it identifies this application, it goes ahead and checks whether these applications actually lend themselves to chaos. Are they annotated for chaos? This happens when your annotation check is true, which is default, by the way. So the first function that the operator performs is identification and filtering of apps upon which you are going to do chaos. The next step is to validate the run properties or the policies that have been mentioned as part of the Chaos engine. You know that in your Chaos engine, you will be specifying a Chaos service account with which you're going to create the Chaos pods, the runner and the experiment pods. So that is what we're calling RBAC in this diagram. So this is the Chaos service account and the associated role. Is this sufficient, or is this actually there on the cluster? And if it is there, then is it good enough to perform the chaos on this application? Does it have the right set of properties? Each experiment is associated with a predetermined set of permissions necessary to execute that chaos. And the operator maps that and identifies or validates whether the Chaos service account is available and is sufficient to run the chaos. The next step it performs, or the next validation it performs, is whether there are any overrides that are present for the experiment tunables. The experiment environment variables and the experiment properties, such as some config maps you want to push to it, or some secrets that you might want to push to it, you can override what is present on the experiment in the engine. You might have some instance specific data that you might want to push dynamically during the run of the experiment. So you push them via the Chaos engine. The operator identifies if there are any overrides in terms of the environment variables or the config or the secret details that are pushed for the experiment, and then takes note of that and incorporates that while it creates the chaos runner, pushes that information when it creates the chaos runner. You can not only override the experiment properties, but you can also override some of the some of the chaos runner attributes as well. When I say chaos runner, that pod also has a particular image, a particular pull policy, and a set of arguments that you run the runner with. Those can also be superseded by the chaos engine, and the operator takes note of that and does the appropriate action. Why this is necessary is in the context of developing new experiments or making infra changes to the framework. Let's say you've pushed some changes to the runner and you want to take a look at how that is behaving. You have an option of pushing your own runner image with the attributes that you want, the pull policy and the arguments that it takes, the command that it has to run as part of the engine override, and the operator takes that into consideration. The operator also takes a look at the job cleanup policy and accordingly cleans up the chaos resources at the end of an experiment run or retains them. The runner and the job pod, the experiment pod, are either cleaned up or retained for further perusal of the user. The operator takes care of that. It also takes care of monitoring. If your chaos engine has set the monitoring to true, then the experiment metrics are monitored. The chaos operator will ensure that these metrics are collected and enables the exporter to scrape them from the engine. It also takes a look at the auxiliary applications that you have specified in your chaos engine. This is especially relevant when you are performing experiments at an infra level or a node level. Examples like node drain or node drain experiments, node level CPU or memory hog experiments, or certain service kill experiments like Docker kill, kubelet service kill experiments, where the blast radius is higher and you not only want your primary application target, the AUT, to be tested, but also several downstream applications that might be depending upon this AUT or might have resided on the node that you are targeting as part of the infra experiment. So this auxiliary application info is passed down along with the other details to the chaos runner, and the experiment executes in such a way that it not only validates your primary application but also the auxiliary applications. And the runner is also aware of the override policies for the experiment, etc. So the second part of the operator's functionality, or the second major function it performs, is to validate and implement certain policies that you might have defined in the chaos engine. The other major factor or the other major function of the operator is reconciling the state of the chaos engine. So there are three states of the chaos engine. We will look at the state diagram in a bit. One is the initialized state, which is when your engine is just created, launched. The completed state, when an experiment execution has completed. It has run its full course. The other state is when you actually stop the chaos engine or you abort the chaos experiment. When you abort the chaos experiment, the operator sets the engine state to stop. And there are some actions in each case. When you do the initialization, there are certain steps that the operator takes. When your experiment execution has completed, it takes a certain number of steps. When you abort it, it takes a certain number of steps. So all these operations are performed by the chaos operator. To recap, it does the identification and validation on filtering of the application. It validates and implements your run policies, and it reconciles the state of the chaos engine. Okay, this is about what it does. The operator itself is written in Golang. It uses the operator framework. We used the operator framework to bootstrap the operator SDK, to be specific, to bootstrap this chaos operator and placed the business logic for performing these actions. It runs as a deployment in the cluster, typically in the Litmus namespace, and it supports chaos on certain native Kubernetes controllers like deployment, stateful set, and daemon set. And it also supports chaos on deployment config resource in OpenShift. When I say supports chaos, we are talking about the nature of these applications. They can be deployments or stateful sets or daemon sets or deployment configs. The chaos operator can also look for custom chaos annotations. We said during the filtering phase, it checks whether the app is annotated. By default, it uses the litmuschaos.io/chaos set to true. You would have seen this or noticed this in the get started video. But you can also push certain custom annotations to this. You might want to have your own way of annotating applications for chaos, and that's something that can be pushed here. And there are three operational modes of the chaos operator. Now, what are these operational modes? There are different personas in Litmus. There is the SRE persona, who is actually generally expected to have autonomy over the clusters. Then there are the developer personas, who might either be using a staging cluster that they are sharing with several other developers, or they might have permissions to execute or be the service owners of some applications or some services, microservices, on the production itself. So there are different types of users of Litmus, and the operator has a specific mode associated with each of these personas. The standard mode is where the Litmus operator runs in a centralized namespace, typically the Litmus namespace, and it watches for chaos engines created across the cluster in different namespaces. Typically, the SRE or the cluster admin or DevOps admin installs Litmus and the CRDs via the Helm install and allows the developers or service owners to pull their own experiments from the chaos hub and create the chaos engines and operate. This is the standard mode. In the admin mode of operation, the SREs or the cluster admins, or sometimes even developers who have their own development clusters, smaller clusters, might install Litmus in a centralized chaos namespace. That is where they will also pull the experiments and create the engines while killing the applications across different namespaces. So sometimes SREs do not want to replicate or pull experiments, chaos experiment CRs into the individual app namespaces and want them collated in a single location while still being able to execute chaos on applications across namespaces. That is the admin mode. The namespace mode is a mode in which the developers are operating in very, very strict environments where they're very conscious of blast radius and they have policies enforced in such a way that they are not able to retrieve or not able to debug or have visibility into what the operator is doing if it is installed in a centralized namespace. So this is a sandboxed kind of an environment where developer has his own quotas, has his own application stack deployed in his namespace, and has absolutely no control over any other namespaces in his cluster, which is when he might want to install the entire Litmus stack also, including the operator, the experiments, engines, everything in the same namespace. In this case, the operator is tuned or set up to watch for chaos engines created only in its namespace and does not have visibility into other namespaces. This way, several developers on a cluster can install their own namespace operators and create the experiment CRs in the same namespace and get the reconcile done there. So these are the details of the chaos operator. We'll take a look at how the state flows in the chaos engine as implemented by the operator. We said there are primarily three states: initialized, completed, and stopped. And this is how the state changes. When a user creates a chaos engine, he is actually the operator is going to trigger the chaos by launching the chaos runner pod. There is a step here that says add finalizer. What does this mean? Now, the chaos operator has a set of child resources, the chaos runner, and also the chaos experiment that the runner creates. These are the child chaos resources associated with a given chaos engine. And the chaos engine resource should be deleted or should be removed only after all its children are removed. That is, when there is a logical conclusion to the experiment run. It could be complete or it could be abort. So the operator ensures that a chaos engine cannot be removed until a logical conclusion has been reached for an experiment run. It does so by using Kubernetes functionality called as finalizers, where the CR is instrumented with a finalizer which is going to be removed, paving the way for the resource deletion, the engine deletion, only after all the child resources have been removed. So when you create the chaos engine as a user, the operator launches the chaos resources. It also creates the finalizer, and once the execution of the experiment has been completed, the runner actually states via the chaos result, which we are going to see shortly, that the experiment has completed. The operator watches for that and sets the engine state to completed, the engine status to completed. At this point, if you reapply the chaos engine, it is going to re-trigger this experiment. It is actually going to perform the same set of steps once again. At the point where the experiment is completed, the operator either retains your chaos pods or removes it depending upon your job cleanup policy. And once it removes the chaos pods, it's actually going to remove the finalizer as well. In fact, after you reapply the chaos engine at this point, it's going to perform the same actions. Or you may choose to delete the chaos engine resource, in which case it's going to stop the reconcile operation. The other flow is the initialized state to a stopped state. So the experiment has been started, it is going on, and you feel that you want to abort the experiment. You can do so in two ways: by setting the engine state to stop via a patch operation, or you can delete the chaos engine. If you have patched the engine for abort, then the operator is going to set the engine status to stopped. There are two properties there is an engine state in the spec of the chaos engine and engine status, as you might have seen during the get started demo. The engine state in the spec is the one that the user patches, and the status is set to stopped or reconciled accordingly based on the patch by the chaos operator. If you reapply the chaos engine from this point, it is going to retrigger the experiment run. As part of the stop or the abort, it deletes the chaos pods forcefully. We saw that in the graceful case, completion case, the pods were either retained or deleted based on the job cleanup policy, and then the finalizer was removed. In this case, the abort case, the chaos pods are all removed forcefully. The finalizer is also removed, paving the way for a retrigger upon reapply. You could also choose to remove the chaos engine at this point, also post the abort. And the reconciles stopped already, and any residual chaos resources, if they are available still and have not been removed, are going to be removed. So this is the way the state flows in the chaos engine, and the operator manages these state transitions. All the icons here that show the gear icon, all the places where the gear icon is shown indicates that these are operations that the chaos operator is performing, while the icons where the indication is for human, these are the operations that a user would perform, things like creating the chaos engine, removing the chaos engine, or reapplying a chaos engine. Okay, so this is about the chaos operator, and we also took a look at the different modes in which it operates. Now we have a closer idea, we have a better idea of what it does as part of its execution. Let's go to the next component under the chaos orchestration category, that is the chaos runner. You have observed in the previous slide that the operator launches the chaos runner. We'll take a look in this and subsequent slide how the chaos runner operates, what it does, and why it is needed. You can see that the runner acts upon a couple of CRs, the chaos experiment CR and the chaos engine CR. Whereas in the operator, you might have noticed that the operator takes a look only at the chaos engine. It reconciles the chaos engine. The operator, which is a secondary resource for the operator, the child resource, reads from the chaos engine as well as the chaos experiment static CR. What it does is it gets the experiment attributes from the chaos experiment. As you all know, the chaos experiment holds a lot of low-level information about the experiment. It talks about what is the image used for the experiment job. It talks about what are the commands and args used in that image. It talks about some operational characteristics, the service account, the security context, host PID, some environment variables, defaults for that experiment, and also if there are some experiment dependencies, such as there is a secret that you need to create on the cluster which is consumed by the experiment, or if there's some config information you want to push, or if the experiment needs some information or data passed in volumes, typically as host paths or host files. All this information is available in the chaos experiment, and the chaos runner reads these attributes. It also gets the override values from the chaos engine, we mentioned that the engine definition can contain overrides for some of the defaults present in the chaos experiment. You can override environment variable values, config maps, secrets, etc. So the runner takes a look at these and obtains the overrides. When I talk about overrides for config map and secret, you may ask, what is the override here really? Here, it is about the config map names. There might be a default that your experiment might specify, but you might have created a different secret or a config which contains information relevant to that instance of chaos, and you might want to push that instead of what is expected by default. That is what we mean by overriding configs and secrets. And it also gets certain instance specific attributes. So in the engine, you can also specify some metadata that you want to associate with that particular instance of the chaos run. When we say instance, each time you create the engine, it's a new instance of chaos. And to categorize or to characterize that particular run of chaos, you might want to push some metadata. You can push a run ID that will be attached or suffixed to all the chaos resources created as part of this chaos. The experiment jobs, the chaos results CR are all going to be appended with a run ID. Sometimes you might have the same experiments and same chaos engine names that you might reuse, and you might not want to patch or rerun or recreate resources with the same names. You might want to create the resources with different names. That is when the run ID is going to be helpful. Sometimes you also want to specify some node affinity policies. You might want your chaos resource pods to get created on a specific node. You might want to specify the node selector where you want the chaos pods to run, the runner and the experiment pods. This is useful sometimes in the context of infra experiments where you don't want to disturb your experiment and runner pods if you are specifying some kind of chaos on that node. You might want to push these pods to some other nodes. That's where node selectors are important. It's also important sometimes to specify anti-affinity policies. You don't want chaos pods to run where some other applications are running, etc. So all these are instance-specific attributes that you can specify in the chaos engine. Your chaos runner also gets these details and accordingly creates your runner and experiment pods. Accordingly creates your experiment pods. It takes into account or into consideration all these values and constructs the experiment job. And once it constructs the experiment job, it launches it. The experiment job is going to create or inject the chaos on your AUT or application under test. And the runner is also going to look for or monitor the chaos job as it runs. So in short, the runner does a lifecycle management of your experiment. It constructs your experiment job, it launches it, and the experiment job does its job of creating the chaos and creating the result. And the runner also monitors for the completion of this job. You might ask why the runner has to create a job and why can't the runner run the experiment itself? It's a fair argument. So chaos engine actually can contain more than one experiment. You can run it in a suite mode where your experiments can be listed in the chaos engine, targeted against the same application, one after another. And your runner acts like an umbrella executor where it does these functions for each experiment specified in the engine and runs them one after another. So the operator delegates these responsibilities to the runner. The runner also does an additional job. It takes a look at or watches for the chaos result that is created by this experiment and derives the status and the verdict of the experiment and patches that back into the engine. You can see here this chaos result is going to be constructed with a name that is a combination of your engine and experiment. The engine named X, experiment named Y, the chaos result is named XY. And of course, you have the option of appending the run IDs to these. The chaos runner looks at the chaos result, derives the information about the status of the experiment and the verdict, and patches that data back into the chaos engine. This way, your chaos engine continues to remain the single source of truth for the user. So if you do a describe of a chaos engine, you will look at the experiments performed as part of that run. You will get the overall engine status which the engine is maintaining. You saw the previous state diagram. And also the individual experiment status which is being patched by the chaos runner. That way you have a whole picture of what is happening. If you want more detailed information about what happened during the course of the experiment, you can take a look at the chaos result. Now, some tidbits about the runner. It is also an infra piece which is written in Golang, and it runs as a pod, not as a deployment, unlike the operator. So we run it as a pod, and the chaos operator always reconciles this. So even if you run it as a pod, in the eventuality of this getting killed, your operator is going to create it once again, and the runner is idempotent, and thereby whatever operations it has already performed will not be repeated if the right state is matched. We look at the state transitions in the chaos experiment status. So this status is also patched back into the engine like we discussed by the runner. The runner is maintaining the experiment statuses in the following manner, and this happens for each experiment as it executes. Initially, once the runner is created, the experiment status is going to contain some details like this. For the sake of illustration, I have skipped a couple of status items and only used or only shown the most important or the relevant ones for our discussion. The experiment status has a field called as pod. This represents the name of the experiment pod, and it has a field called experiment status which talks about the current status of the experiment, and then it also has the verdict of the experiment. Now, the experiment pod is a useful one because it allows tools that are automatically creating the chaos engines, or if you have any parsers that you've written, you can take a look at the pod name. You can derive the pod name directly from the chaos engine, and you can do things like get the events for that pod or get the logs for that pod, etc. The experiment status gives you the exact detail of where we are in the experiment execution. The verdict is filled at the end of the experiment. So the first state here, when the chaos runner is created, is yet to be launched for pod, waiting for the job in terms of status and not applicable for verdict. The chaos runner is now constructing, launching and monitoring your chaos job, at which point you have the actual pod name being patched, you have the status set to running, and the verdict is set to awaited. This is the point where your experiment is currently running. And once your experiment execution has completed, either it has passed or it may have failed, depending upon the kind of checks you have in your experiment. The experiment pod name continues to be available. Your status is now set to completed, and the verdict is going to be either pass or fail. At this point, the runner may either continue to stay in the cluster in completed state. The pod might continue to stay in completed state if your job cleanup policy mentions retain. or it might be deleted automatically if your job cleanup policy says delete. There's also the other alternate workflow, alternate state, where over the course of the execution, you might set it to a bot, which we saw in the previous slides, in which case your runner is going to be immediately removed. It's going to be force deleted, okay? And your experiment at that point is going to be set to stopped. Your experiment status is going to be set to stopped, and your engine status is also going to be set to stopped. The operator takes care of that because your runner is no longer alive. It's been force removed. And once we are in this state, the completed or stopped state, a reapplication of your chaos engine is going to recreate your runner. A new instance of the runner is going to be created, and the cycle starts again. It's also possible that your experiment CR might not be found. So when your runner is executed and it does not find the experiment CR to read from or get the attributes from, in that case, it's going to say the pod is not there, it's not applicable. Your experiment CR has not been found. That is the status, and your verdict is fail. Your experiment run is fail, and your experiment is missing. That's what happens from this point if the experiment is missing. And if you reapply the chaos engine once again after you have pulled the experiment into that namespace, then the cycle is going to get started once again. So these are the various state transitions of the chaos engine in terms of experiment status as carried out by the chaos runner. So now you have a fair idea of the chaos runner, which is a child resource of the chaos operator. Next, we'll go to the chaos experiment. The chaos experiment flowchart is familiar to you. You have taken a look at this in our previous episodes. We will just run through that once again. The focus here in this session is about the characteristics of the experiment, or what you can do with your chaos experiments, how they are written and how you can describe them, etc., more than the flow. The flow is something that you're already aware of. The library for chaos, the chaos tunables, such as the chaos targets, the duration, the intervals, etc. The app information is all passed down in the job by the chaos runner. And these are processed, and the experiment result is set initialized. A set of steady state checks are performed on the application and the auxiliary applications which you might have provided. The experiment does these status checks and creates relevant events upon completion of these checks. A pre-chaos event is generated when the steady state check has completed. If your checks fail, your steady state checks fail, then the experiment is going to end with a summary event describing this failure of the steady state, and it's going to patch the chaos result with appropriate information. And your runner is going to patch that back into the engine, and the status is going to be completed, as we saw earlier. If these go through, then your chaos resources are launched. When we say chaos resources are launched, some experiments make use of helper resources to do chaos. Sometimes the experiment pod itself injects the chaos, mostly. And the chaos is iterated. You might have specified the chaos to happen for a certain duration over some intervals. So the kills or the latencies or the crashes happen according to the specification on your chaos engine, according to the interval. And each iteration of the injection is associated with the chaos inject event that you can catch. And then you revert or clean up chaos. You perform post-chaos checks. Post-chaos checks typically look at your application state, your auxiliary application state, and also in upcoming releases, certain probes that you might have specified for your chaos engine. When I say probes, these are some custom conditions that you might want fulfilled not just application status that you're checking after chaos, but also you're looking for a certain condition to be fulfilled on your cluster, on your application after chaos or during chaos. And then you generate a post-chaos event capturing this detail. And accordingly, based on these post-chaos checks, you're either going to fail your experiment or you're going to pass it. This information is patched back into your chaos result. The runner takes this information back to the chaos engine. This is something that you already know, but what is interesting and what I would like to describe during this session about experiments is that unlike the chaos operator or the chaos runner, which are infra pieces and are written in Go, the experiment is something that you can write a language of your choice. You can use any language that you want, and you can containerize your chaos logic and start using that. And you can have Litmus orchestrate that. Having said that, you have bootstrap support today for chaos experiments in Golang, Ansible, and in Python. When I say bootstrap support, we have some scaffolding tools which will help you to generate the experiment code artifacts. You will have a Python file, Python script, or an Ansible playbook, and a Golang file, created.go file, scaffolded for you with all the standard functions representing these states: the engine initialization, steady state checks, chaos injection, post chaos, and the final engine patch, the result patch. The functions for doing each of these is already bootstrapped available for you, along with the necessary statements to generate the events or do all the miscellaneous stuff. And you can go and fill in the business logic inside these functions. It makes your experience of creating an experiment simpler. The bootstrap support is there for Golang, Ansible, and Python. Coming to the experiments, the way they run is as job, like you know. This was a conscious decision in Litmus. Most of the times you want chaos executed as one-time operations. You might want to schedule it every time, or sometimes that is available, that is supported via the chaos scheduler, but the instance of chaos is typically run as a one-time action, so it runs as a Kubernetes job. Like I mentioned, Litmus supports the BYOC model, or the bring your own chaos model, where you might have some existing chaos logic using some of the tools you might have built already or you might have pulled from the existing vibrant chaos ecosystem and created your chaos logic. You can, with very minimal instrumentation, use that within Litmus. You saw that the experiment has an attribute for the image and args and command. So you can containerize your chaos logic and provide the image along with the right entry points, commands, and arguments with your own environment variables, and Litmus is going to take care of running that. The runner is going to launch that job. It's going to do the same management. It's going to construct the job based on how you've specified your chaos experiment. It's going to launch and monitor it, and it's going to report the status back into the engine. There are many users who are using Litmus with both the native experiments as well as the BYOC mode of execution. As you know, the experiment generates the chaos result resource, custom resource. It is a runtime created resource. And the experiment business logic itself is crystallized or described in the chaos experiment CR. It is a static CR which is read by the runner and is available on the Chaos Hub, something that's off the shelf and pullable. All right, so this is about the characteristics of the experiment. The next thing we will discuss is chaos monitoring. The next moving part or the next component in Litmus is the monitoring deployments, the metrics and the event exporter. Before going to what they are, I just want to take a minute in explaining how they are useful. As you all know, chaos is nothing without observability. You need monitoring in order to tell what has happened to your application, how it has behaved when a certain failure has happened. So chaos and observability go hand in hand. They are inseparable. So we want to support some ways in which you can hook Litmus Chaos runs into your existing monitoring infrastructure. You might already be using Prometheus, Grafana, you might be using other monitoring mechanisms, CloudWatch and AWS, for example. You might be using Datadog or Sysdig. Litmus provides certain visibility into how your chaos is running. Not only do the chaos runner and operator and experiment pods do the orchestration and execution of chaos, they also keep generating events from time to time at each stage. We saw some of the events getting generated during the experiment, but I did not mention that the events are also generated by the chaos runner and the chaos operator during each state transition. So we've made use of the event exporter from Heptio, which is a really nifty tool. With the HTTP sync, the event router converts these Kubernetes events into chaos metrics. They are converted into Prometheus metrics. And if you already have Prometheus set up, you can scrape the event router service and you can get the chaos events via the appropriate filters. You can set the involved object to the chaos engine and you can keep getting the status of the experiment run as it happens. You can use that information to overlay the chaos events on top of existing application dashboards. In this example that I've shown on this slide, there is a sock shop application that was run on the cluster, and there was the Grafana dashboards set up to monitoring the queries per second and the latency of several microservices like orders and catalogs. And the metrics coming out of the event router were used to figure out when the chaos is occurring and for how long it occurs. And using this, you can see, you can overlay the chaos events on top of your existing application dashboards. You can see the latency spikes for the catalog service exactly at the time the chaos is injected. So you can find out what your application is doing, how it is behaving when chaos happens using this mechanism. So you can find the event exporter, of course, tuned for Litmus in the observability repo of Litmus. We'll take a look at that very shortly. The other component in chaos monitoring in Litmus is the metrics exporter. Now, what is the difference between the events and the metrics exporter? Not only do you want to find out the progress of the experiment, what is happening during each stage, and thereby find out what is happening on your app, you also need some analytics. You also need to find out over a period of time how your experiments have fared. for certain clusters, for certain applications, or for certain namespaces, you want to see how many experiments were executed, how many passed, how many failed, how many are in queue, and that is going to give you an information about the overall resiliency of your cluster or your application. It's very indicative of how you are running your application on your production or staging clusters. What is the measure of its resiliency? What is the measure of its stability? This information can be pretty useful in deriving meta information that is going to be probably used by different personas within the organization when looking at long-term stability of or long-term operational stability of your clusters or applications. So that is the metrics exporter. Both the event and metrics exporter contribute to different facets of observability in chaos engineering in Litmus chaos experiments. So these are the moving parts. Let's put all this information together. You must be familiar with this slide. We talked about it in our architectural overview. A swim lane diagram that is giving you a complete picture of what's happening. The user actions involve creation of a chaos engine after he's pulled the experiment CR, and that is going to lead the operator to launch the chaos runner, which manages the lifecycle of the experiment. The runner is going to do experiment dependency checks. It is going to take into consideration the overrides, operating characteristics, and launch the experiment job, run the experiment. The experiment creates a CR, the result CR, which the runner is going to view to patch the status back into the chaos engine. You can also, the user also can abort the experiment, which will in turn remove the chaos runner and the experiment pods, and the status is going to be set accordingly. And as these operations happen, your chaos exporters, the event and the metric exporters, are gathering details about the experiment runs. The various happenings are caught by the experiment, the chaos exporters. So this is one slide that is illustrating the overall execution workflow. One of the things of interest about aborting experiments is there are some experiments which launch certain processes within target containers. For example, pod CPU hogs or memory hog experiments launch certain processes within the chaos targets. You might be running a sock shop application with the catalog service and have caused a CPU or a memory hog in the catalog service by launching certain processes within that. Now, when I abort, not only do I want the experiment and runner pods to be removed, but I also want those processes to be stopped. These are requirements are something that are handled within the experiment via appropriate procedures. You cache the signal terminations coming to the chaos pods and accordingly terminate these processes you might have started on the target containers and then get killed. On a case-by-case basis, these are managed within the experiment logic. Now, we've come to the end of this session talking about the experiment workflow where the different components play a part, the operator, runner, and the experiment pods, what roles they perform, what are the state transitions that take place in the chaos engine carried out by these respective components. And you also took a look at some details about these components in terms of how they are written and how they are represented, etc. Let me talk about the special interest groups in Litmus for a second briefly. You saw all these components. A lot of community members have interest in contributing to these components because they want to integrate their solutions with Litmus, and those integration points fall into one of these components. So we decided to start some special interest groups where there can be some focused effort by interested community members around the growth of the individual components and thereby the overall Litmus experience. And these groups have the responsibility of driving the roadmap for those components, and thereby they form an extended product management team for the Litmus project itself. Each SIG has a definite charter with very specific goals and the meeting cadence specified for that SIG. And these components and thereby the associated GitHub repositories, the Docker images, etc., fall under the purview of the respective SIG. The SIG orchestration, the SIG chaos, the SIG observability, SIG documentation, SIG deployment, SIG integrations, and SIG testing are the current planned and operational SIGs. They have these repositories specified within them. There are GitHub teams in the Litmus GitHub org that are comprising the community members who are interested in contributing and participating in the development of these components. Some of these SIGs cut across components as well. For example, the documentation and the testing SIGs also take a look at not just one component, but take a look at the project as a whole, with contributions coming in from the required or the specific respective SIGs for content, the testing, the test cases, the testing business logic. The documentation comes from the respective SIGs, but is created and accepted into the project by the SIG documentation and the SIG testing teams. So a charter of a SIG looks something like this. Let me take a look at that. Let me show you that. You can see that it has a specific set of goals. I'm taking the example of the integrations SIG, where there might be members who are using Litmus to orchestrate the chaos experiments, their own chaos experiments using the BYOC model. They might be using other tools. There are some members who might be using other abstractions to run Litmus. For example, the engines might be created using Argo workflows, for example. So in this case, the goals are to maintain these plugins and provide the corresponding documentation and tests and specify the CI and E2E processes for that, provide the governance for the repositories under the purview of the SIG, and also participate in the Slack channel. There are SIG chairs or leads for every SIG. The non-goals are also specified explicitly, and then the repositories under that SIG are also specified. You can see that the components have their respective repositories which the SIG team maintains. You have the operator, which is available in the LitmusChaos org as LitmusChaos/chaos operator. The folder structure of these repositories, the CI processes for these repositories, the contributing guidelines for these components are all specified here in the respective repositories. The chaos runner is another separate repository consisting of details for the chaos runner, and the chaos experiments are available in the Litmus Go, the Litmus Ansible, and in Litmus Python. You can take a look at the structure of the experiments. In all three languages, the experiments are structured in a similar way. The folders are also arranged in a very identical way in terms of how you have the various functions distributed. You have the generic chaos experiments in Litmus Go, where each experiment consists of its own folder, and these also find representation in the chaos lib, where you're going to see the injection logic present here, while the experiments folder consists of the overall flow for this experiment. You can take a closer look at these repositories, and in subsequent episodes, we'll also cover how you can construct your own experiments, how you can bootstrap an experiment, how you can run, how you can test your experiment, how you can develop business logic for experiments, and how you can test them, and how you can provide them as a chaos chart. The entire the contribution workflow will be discussed in a separate episode. The observability has its own folders inside of the Litmus repo where you add several sample applications and readily available dashboards for these applications. You can find them here. And the documentation has the Litmus docs repository. These docs are also represented in the docs website, which is docs.litmuschaos.io, and the source is available here. The SIG integrations has several repositories. I'm going to show one, the chaos workflows, which run Argo workflows with chaos. We are going to talk about how this can be done, or how workflows can create chaos, in another episode. And the SIG testing consists of the Litmus E2E repository, where you have several branches which are talking about the different pipelines available within Litmus for different categories of experiments. So I just wanted to introduce to you the special interest groups and the various repositories within Litmus. And now that you have a good idea of the components and how they behave, you can also take a look at these repositories for more details around some internals, and also to contribute or to enhance these components. That's all we have for this session. In subsequent sessions, we will take a closer look at how you can do, how you can weave together several chaos experiments as part of workflows, and how you can integrate Litmus with other CI/CD tools, and what are the different ways you can monitor, what are some useful queries that you can construct out of the chaos metrics and the event metrics that will help you to visualize your application behavior better. So stay tuned for more tutorials. Thank you.